40 kilometers beneath your feet, the rocks begin to flow like glass in a slow oven. And 5,000 kilometers down, iron is hot enough to glow white, yet squeezed so hard, it behaves like solid crystal. We live on the skin of a planet we have never truly entered. The deepest humans have ever physically drilled into Earth is the Kola super deep borehole in Russia, about 12 kilometers down. That's less than 0.2% of the way to the center. If Earth were a standard 30-centimeter globe, our deepest hole would barely scratch half a millimeter into the paint. And yet, with that tiny pinprick of access, plus some very clever physics, we now have a surprisingly detailed picture of what's really inside. For centuries, though, that inner world was not a scientific landscape. It was a blank canvas for myth, religion, and adventure stories. If you go back a few hundred years, down meant more than just direction. Many cultures imagined the underworld literally beneath the surface, a realm of ancestors, gods, demons, or punishment. The ancient Greeks placed Hades below. Norse mythology had hell. Christianity imagined hell beneath our feet. These ideas were not based on geology. They were metaphors anchored to a simple observation. Dig, and the world gets darker, hotter, and stranger. You don't need instruments to notice that. Anyone who has walked into a deep cave or descended into a mine has felt the air grow warm and heavy, the rocks sweating moisture, the ceiling pressing psychologically closer even when it's meters above your head. For early humans, down was alien territory, and alien territory invites stories. By the 18th and 19th centuries, we began to actually measure that underground strangeness. Miners and scientists noticed a pattern called the geothermal gradient. As you go deeper, the temperature rises, on average, about 25 to 30 degrees Celsius per kilometer in the upper crust. In some mines, it became dangerously hot just a few kilometers down. This posed a puzzle. If the temperature kept rising at that same rate all the way to the center, the core would be tens of thousands of degrees, hotter than the surface of the sun, which is unrealistic. So, either the gradient must change with depth, or something in our understanding was very wrong. Either way, the Earth was not a simple cold block with some fire at the bottom. It was more like a layered thermal engine whose details we were only beginning to glimpse. Around the same time, physics was quietly demolishing one of the oldest pictures of Earth's interior. For a long time, some scientists thought the planet might be mostly molten inside, with a thin solid crust floating on a global ocean of magma. That would explain volcanoes, cracks in the shell where the inner ocean leaked out. But in the late 19th century, Lord Kelvin and others did a back-of-the-envelope calculation using heat conduction. If Earth had started off molten and were now just cooling like a hot iron ball in cold water, it should have solidified and cooled to near-present temperatures in only tens of millions of years. Geology and early biology were already pointing to a much older planet. Something didn't add up. That something turned out to be radioactivity. In the early 20th century, we discovered that unstable isotopes of uranium, thorium, and potassium inside Earth were continuously decaying, releasing heat. The planet wasn't just cooling, it had an internal furnace. The inner Earth was not a static arrangement of layers, it was dynamic, powered. So, by the early 1900s, scientists knew three crucial things. 1. Heat increases with depth near the surface. 2. That heat cannot simply be left over from Earth's formation. It is being topped up by radioactive decay. And 3. The bulk of Earth must be solid enough to support mountains and transmit vibrations efficiently. That last clue came from earthquakes. Every tremor is like a giant accidental ultrasound scan of the planet. When a large quake happens, it sends out seismic waves, ripples of mechanical energy that propagate through the interior. There are two main types of body waves: P waves or primary waves, which are compressional like sound and can travel through solids, liquids, and gases, and S waves or secondary shear waves, which involve sideways motion and can only travel through solids. By recording how fast these waves arrived at seismometers scattered across the globe and which paths they could and couldn't take, scientists could infer not just that Earth is layered, but what state, solid or liquid, those layers must be. In 1906, the scientist Richard Dixon Oldham noticed something odd. S-waves simply vanished beyond a certain angular distance from large earthquakes. It was as if they hit an invisible boundary and could not cross. Meanwhile, P-waves were slowed and refracted, bent, as they passed through some inner region. The simplest explanation? Earth has a liquid layer deep inside. Later, in 1936, Inge Lehmann, a Danish seismologist, analyzed subtle reflections and refractions of P-waves and proposed that within the liquid region lurks a smaller solid sphere, the inner core. This was not guesswork. It was reverse engineering. Imagine having only the pattern of ripples on the surface of a pond when stones are thrown in, and from that, reconstructing the shape of hidden obstacles beneath the water. That is essentially what seismologists did for the entire planet. But while scientists were painstakingly charting real layers using wave speeds and thermodynamics, popular imagination was racing ahead in a different direction. In 1864, Jules Verne published Journey to the Center of the Earth, and he did something brilliant. He took the limited geological knowledge of his time, the idea of underground caverns, ancient fossils in deep rock, volcanic conduits, and stretched them just enough to create a plausible-feeling fantasy. His characters descend into an Icelandic volcano, walk for weeks through a gigantic subterranean gallery, and eventually discover a vast underground ocean with prehistoric creatures. Geologically, this is nonsense. The pressures and temperatures at those depths would crush and cook any such cavity. There is no open space, no air-filled cathedral, where a 19th-century explorer could simply stroll by torchlight. But Verne's story did something important. It cemented the idea of the Earth's interior as a destination. Not just a set of abstract layers on a diagram, but a place you could, in principle, visit. A place with weather, ecosystems, and landscapes just hidden below. Science fiction kept returning to that theme: caverns under our feet, hollow planets, lost worlds illuminated by hidden suns. Even when the details were absurd, the emotional appeal was real. Going down is the inverse of going to space. Space is cold, empty, inhospitable. The imagined underworld is enclosed, secret, perhaps survivable. It feels like trespassing into the body of the planet itself. Modern geology, of course, paints a far harsher picture. At 100 kilometers down, pressures exceed 3 gigapascals, that's 30,000 times atmospheric pressure, and temperatures likely past 1200 degrees Celsius. Rock there can still flow, but only if you give it thousands to millions of years. On human timescales, it feels rigid. At 1,000 kilometers, the pressure rises above 40 gigapascals, and exotic mineral phases like bridgemanite become stable. By the time you're near the core mantle boundary, around 2,900 kilometers down, the pressure hits about 135 gigapascals, and the temperature may exceed 3,500 to 4,000 degrees. There is no space for air-filled caves. The rock is dense, hot, and under unimaginable squeeze.